I'm Andrei Chumak. I work as a faculty of physics, University of Vienna. And in this mini lecture, I would like to speak about spin waves. So my task for today is to try to explain what a spin wave is in the simplest possible way. This course is oriented to students who study physics at universities, and ideally would be if you listened already atom physics or solid state physics, but if it's not the case, but you still know already mechanics, electrodynamics, you still should be able to understand the material presented here. So let us go. Let me first share my screen. Okay, so the topic of today's video, basics of spin waves. And since I'm going to speak today about oscillations and waves, it's kind of logical to start with refreshing your memories what a harmonic oscillator is. Okay, let us consider the following physical problem. We have a body of mass m which hangs on such a spring. And this spring has a coefficient of elasticity k, and in addition we place here a coordinate axis x pointing into this direction along the spring, and x equals 0 point we choose the equilibrium point, like it's shown here. So if you do not touch this body, it will be hanging in this position. This is our steady state. Now what you need to do, you have to take into account two forces. First of all is gravitational force, which is trying to pull your body down as much as possible. But there is also a force of elasticity of your spring, which pulls it up. And in the case of equilibrium, like it's shown here, these two forces are equal. So the length of these vectors is the same. And that's why body is staying there without motion. So how this force, elasticity force, is defined? For this, we need Hooke's law, who says that force needed to extend or compress a spring scales linearly with respect to the displacement. So principally, his main message is that this force is proportional to the displacement x, or to coordinate x, but in this system of coordinate, you see that x can be positive or can be negative, and principally it measures the displacement, because if L0 is the original length of your spring, x just gives you the difference. So this is the real length with respect to original. Good. So main point is that this force is proportional to coordinate x, and it's also very important. There is minus sign here, which clearly tells you that if you stretch your spring, force will be pointing in the opposite direction, and if you compress your spring, force again points in the opposite direction. That's why we need here this minus. And what's also important that this elasticity force depends on the displacement and mg does not. Okay, afterwards, what we do, we just write the second Newton's law, and we know that force is equal mass times acceleration. So at the university, you already studied that the acceleration is second derivative of the displacement coordinate over time, or you can write it also in such a form, x with 2 points. And on the right side of equation, I just write these two forces. So here you see our mg, and here you see Hooke's law. The only difference here, you see that I have added here some displacement. So you can do it properly. For this, you would have to switch to another system of coordinates. When you remove this m, you see where your spring, it will be pushed up a bit, then the equilibrium will be at some other point, and then you would switch back to our system of coordinate. So instead of doing all this, you can simply analyzing initial conditions. You can show that you need to take into account such a displacement delta x, which is mg over k, and I just immediately have written it here. And in such a way, then if you will write x plus mg over k, this k disappears here, and this mg compensates this mg. And you are coming to this very simplest equation of motion of harmonic oscillator, mx 2 points times kx. So you could do this system a bit easier. You could get rid of mg at all if you take it with your spring in a horizontal position, and you would use some oil or some very some surface where you can ignore tension force, then it would be even easier. You would immediately get this equation without using any mg. Good. So this is our equation of motion. I put it here, and I immediately can say that it can be rewritten. Pretty often it's rewritten in more general form when m is moved to this side, and here it's replaced with omega 0 squared. Of course, now we need to solve this equation, and for this what we do, we just use for a solution in such a form when we put a sinus or cosine omega t plus v0. And if you will put such solution into equation here, then just with the simplest mathematics, you can immediately show that resonance frequency here is equal k over m. But the most important is that now you understand that this displacement changes periodically as a sinus or cosine function, and everything what changes such ideally periodically is named harmonic oscillation. Yeah, so this is our harmonic oscillation. That's the physical process which we are describing here. And as you see in this omega, you can immediately see that if you will take the spring, for example, thicker or stronger, then the frequency of oscillations will be larger, so it will be very fast oscillation. But if you will use a heavier mass, you increase mass, the oscillation will be slowly and slowly. And that's exactly what you see here by this dependence. So if to speak about this amplitude A and this original phase V0, it's all defined by the initial conditions. So in order to do this experiment, you need to bring your system out of equilibrium, and depending how far away you will pull it and in which position, it will give you amplitude and V0. So at t.0, that's what matters. Okay, and again, what we have here, this is plotted the displacement x. So you see it can be positive, it can be negative as a function of time. And then we have such a nice sinusoid. And which parameters we have here? Circular frequency omega, which is square root k over m. Pretty often people also work with a linear frequency, f, which is omega divided by 2 pi, and f is measured in hertz. So it means how many repetitions, periods you have per second. And 1 over f parameter, it's nothing else as a period of our oscillation, so time which takes our body to move from one point to exactly the same point, and it simply can be found as 1 over f. Good, so this is our harmonic oscillator, and before we move on, let us have a look where we meet oscillators in our everyday life. And principally, there are many examples. It's really important in our life. It's swing, it's pendulum, and this watch, for example. It's musical instruments. Here we have either oscillations or standing waves. Heart, it's not harmonic oscillator, as you can see, it's not sinus. Nevertheless, it's periodic oscillations and a very important one. And here, car shock absorbers, of course, this are not oscillations. Only if you have this hills periodically distributed, then you will get periodical distribution. But what is harmonic here is oscillations of the wheel. So when it jumps up, wheel is oscillating periodically, but with large absorption. That's especially done in such a way. Okay, and now I would like to switch to one concrete task of oscillation, which is named mechanical precession. Now we consider such a disk, heavy, so it has some mass uniformly distributed over this volume, and this disk can rotate about this axis, which is shown here. Yeah, and it's fixed here, and this end is free. It can be moved here in space. Then as soon as this disk rotates, we can introduce such a physical parameter, which is named angular momentum. So you know that momentum P, it's nothing else as mass time v, speed, velocity. So it means that we take some point, it moves, it has linear momentum, and then we just multiply this linear momentum with a coordinate vector r, like it's shown here. So we need to find here a cross product, and in such a way we can define an angular momentum. So if you take into account all body, angular momentum is pointing along the axis of rotation, like it's shown here, and depending in which direction your disk is rotating, one or another, it will be pointing here or in opposite direction. And the length of this vector, as you can see here, depends by mass and velocity. So it means the faster rotation of your disk is, the larger is angular momentum, or the heavier your disk is, the larger the angular momentum is. Let us have a look how you would search for a time evolution of this angular momentum. What you do, you just take derivative over time, and then you do standard mathematics, R cross product P. So it means that first you search derivative from the first part, time cross product P plus R cross product dP over dt. And let us have a look on this part. Where dr over dt is pointing. So this is the coordinate vector change. It means that there was some body, we had coordinate vector like this, then after some time this point moved here, and we have coordinate vector like that. The delta r, the change is pointing in this direction, more or less it points in the direction where our point was moving. And have a look where p is the point, and p is nothing else as mv, velocity, and it also points in the same direction because that's exactly in which direction our point is moving. And it means that these two vectors, dr over dt and p, points in the same direction, and their cross product is equal to 0. Let us have a look on the second part, and what you see here is that this dp over dt, it's nothing else as a force, yeah, because mv and dv over dt, it's a acceleration. Therefore, this part is our force according to second Newton's law, and you can immediately rewrite the change in the variation of angular momentum in time is equal to the coordinate vector cross product force. And force, and this is by definition a torque. So it means that we have got such a very simple equation that variation in the angular momentum in time is equal to torque. What does it mean physically? Physically, it means the following. So imagine you have the spinning top, and now angle, it's not ideally vertical, but there is already some angle between them. In this case, force mg is trying to pull this top down, but because it has angular momentum, instead of the simplest motion down, what we will get a torque pointing in that direction. And due to this torque, our motion will be working like this. So this is main operational principle of gyroscope, which you probably heard about. And this is a very important physics for us today to understand what a spin wave is. So imagine you have, this is the spinning top, so I believe everybody of you did this experiment. And imagine that you have not one single top, but many of them on this plane. And they interact in a way that this precession, mechanical precession, start to distribute. And as you see this one, and more start to precess, and then you see that there is a wave running from this corner to the top right corner, like it's shown. And this is the easiest for understanding analogy of a spin wave, which is a topic of our discussion today. So we will come back to this point a bit later. Good, but before, let us recall where else we meet spin waves in our life. Imagine that you touch water or you throw a stone into water, you will immediately have a water wave. You know that X-ray, it's a wave. You know that light, it's a wave, which we have principally, these are both particular cases of electromagnetic wave. And electromagnetic wave is used everywhere in our life. So the most important nowadays probably are smartphones and our Wi-Fi. Yeah. So besides, we hear also waves. These are waves in the density of the air. That's exactly what we feel. Or you can even create such artificial wave. This is of course more a joke because this if you describe it physically, it's really a forced excitation, a forced wave, and people define the period and all parameters of this wave. But if to be serious, you see that principally a wave in general plays a crucial role for a human being, especially in sense of communication, because we hear waves, we see waves, our cell phone works because of waves, internet also works because of waves. First you send information in a fiber in the form of light, and afterwards you again convert it into gigahertz range electromagnetic wave from your Wi-Fi router. So wave is everywhere. Good. But now I would like to make a step from mechanics to solid state physics. In particular, I would like to explain what is magnetization precession. So now what we do, we are switching from this bulky, massive spinning top to an atom. So you know probably already the Bohr model of atom, who says that there is an electron, and this electron rotates around positively charged nucleus. In terms of scales, what we do now, we decrease sizes of our model hundreds billions times, and we increase speeds 100 billions times. So everything is getting very small and very fast. So this is named atomic scale. But the first step, you know that electron, it's a charged particle, and charge is the most important, but it also has some mass. As soon as it has some mass, it means that we can simply one-to-one copy the formula which we had already from the previous, from mechanics, because it's just a body of mass m which rotates around some axis, and it means that it has orbital angular momentum. Nevertheless, in addition to this orbital angular momentum, we also have so-called spin of electron. And the easiest of this is purely quantum mechanical issue, but the easiest way to understand it, to look on it like this is our Earth, which rotates around the Sun, but besides, and this is our orbital momentum, but besides, Earth rotates on its own about its axis. That's why we have day and night. And when you have such rotation, the easiest way to understand what spin is, you also will get some mechanical angular momentum. And this is named spin. So the message here is that we still can use the same formula, as that the variation of torque in time is equal angular momentum in time is equal to a torque, but with a difference that now we take into account the so-called total orbital momentum, which takes into account both spin and orbital angular momentum. That's the first point. Second is, you probably all had this very simple experiment. You just take a compass which has arrow and you bring magnet next to it, and compass moves. So this means that you have compass has some magnetic momentum, first of all. And this magnetic momentum of the compass arrow is always strongly coupled in atomic scale to the orbital momentum yacht latch with such a parameter gamma, which is a ferromagnetic ratio. So it's a separate story, but in many cases this is just fundamental constant which depends on Landau factor, on charge of electron, and on its mass. But they're always coupled, and there is a sign minus which is related to the fact that electron is negatively charged. That means that if it has an orbital momentum pointing in one direction, magnetic moment will be pointing in the opposite direction. But now coming back to the compass arrow mu in a magnetic field B, it rotates. It means that magnetic field creates a torque which acts on our magnetic moment. And this is also the formula which you probably know from magnetism, from basics of electrodynamics. The torque is equal mu cross product B, like it's shown here. And this is this torque. Yeah? And the final step we need to take into account, we need to switch from a single atom to the real body. And in this case, what we do, we introduce such parameter which is named magnetization. So magnetization, it's a total magnetic moment. So it means that you just summarize all magnetic moments you have and divide it by the volume of your material. So N large here, it's a density of magnetic moments. So volume is already sitting here. And in this case, then you just do some mathematical routine, you rewrite all this, and then what you do, you plug this torque into this equation, which you got, and instead of this angular momentum, you put J in terms of magnetization. And then what you have, you will get so-called famous Landau-Lifshitz torque equation, which shows you that magnetization changes in time, like cross product of magnetization times applied magnetic induction B. And here is ferromagnetic ratio staying here. Okay, so this is our Landau-Lifshitz torque equation, and the question, what does it mean physically? Again, it means that if you take now magnetic material, so make sure that here usually people are speaking about ferromagnets. In reality, this model can be work for other types of materials, but let us focus on ferromagnet. And ferromagnet is such material which has spontaneous magnetization. So it means that if you magnetize it and then you remove magnetic field, you will get such magnetization M when all or most of the magnetic moments pointing in the same direction. That happens due to so-called exchange interaction. Principally describes that what we know as a magnet. Yeah, that's that magnet which we use on whiteboard or we were playing as we were kids. If you will now take your magnet and will apply some magnetic field H, magnetization will be oriented along this direction if H is large enough. But the story is getting interesting if there is a certain angle between H and M, like it's shown here. Because exactly like remember in the case of spinning top, when it was precession at the very beginning, when you play it, it just stays vertical and nothing happens. But at some point when you have angle, force mg is trying to put it down and it starts to precess. Yeah? The same here, as soon as you have some angle, but now mg doesn't play a role, what plays a role that this field H is trying to pull it back to its direction. But again, since we have this torque equation, what will happen, we will get, instead we will just get a torque point in that direction, and we will get such a motion as you see in this nice animation made by Dmitry Bashko. And now we should also keep in mind that as long as you have excited magnetization precession, it will not stay there forever. So all physical processes, they have damping. So at the end of the day, all our energy will be moved to phononic temperature, phononic oscillation, so to temperature of your solid body. And there are different ways how you can describe damping, but what we usually do, we just use so-called Gilbert damping term. Here alpha is a Gilbert parameter, and inverse value of alpha simply shows you approximately how many oscillations you have before they will be damped. So if your alpha is 10 to the power minus 3, it means that you will have 1000 precessions before it will damp. And physically, this damping means following, so the length of vector m should be conserved, therefore it just draws such a spiral like it is shown in this animation. Good. Now we are ready to jump to spin waves and to magnons. So imagine you have this situation, you have solid body, you magnetized it. Now the question, how to get angle between M and H? It's not so easy an experiment. What we usually do, we just apply small alternating field, and this field also creates a torque, but such that changes angle, and then it increases and increases angle of precession, like it's shown in the animation. And again, if it's plain film, for example, there are many magnetic moments and they talk to each other, like it's shown here. It means that this neighboring are starting to move. You remember this animation with spinning tops, and this is exactly the same. This also start to precess, and we will get wave propagating from this corner to this corner in this simple animation. Then what you do, you of course can find two planes where spins here and here, these magnetic moments here and here are precessing in phase, and distance between them, which will be your wavelength, as well as in any other wave. And there is also wave vector, which usually not always the case for spin waves, but usually point in the direction of propagation. Also, you might hear that such a term of magnon. So what is magnon? Magnon is a quasi-particle of a spin wave. You know that you can describe light. In some cases, it's better to describe it like electromagnetic wave. In some other cases, it's better to describe it as a flow of photons. So photon is a quasi-particle of light, phonon is a quasi-particle of sound, and magnon is a quasi-particle of a spin wave. Again, from quantum mechanics, you know probably, or you will study soon, that energy of any quasi-particle can be found as h omega, so Planck constant times frequency. Quasi-momentum is hk. K, we will come to this. This is a wave number of your magnon. Any quasi-particle has a mass. So just doing this the simplest routine, you know that mass, it's either you find it as 1 over second derivative from dispersion curve, or you can do just the simplest mass here, as it's shown. You just replace this omega with the simplest dispersion curve at a k square. So this is for the case of pure exchange waves. A dispersion of spin wave simply parabola. And then you can easily show that mass can be found in such a form where eta is exchange constant of your magnetic material. And in the case of yttrium iron garnet, for example, such as very often used material in the field of spin waves, mass of magnon, I think 5 times larger than mass of electron. So it's a rather light quasi-particle. And spin of magnon is equal 1. So spin magnon is a boson. That's why we are always happy to study such phenomena as Bose-Einstein condensation and so on. But so much about magnons. And finally, what I would like to say here that we need, of course, to understand what energy contributes to the spin wave. So you remember this many coupled magnetic moments. What couples them? And here there are two main contributions we need to take into account. The first one is exchange energy. So this is part of Coulomb energy, which depends on the orientation of spin of electron. Very strong interaction can be described only by if you understand quantum mechanics. But main idea is that this is that interaction which is responsible principally that we have magnetic material, yes, that our magnet has a spontaneous magnetization. And usually exchange interactions in ferromagnetic material just want to keep all your spins parallel. And as soon as you try to change angle, it increases energy. And besides, you have so-called dipolar energy. Dipolar energy you can understand if you have compass arrows and you will put many of them close. Then you change orientation of one compass arrow and all other will also start to rotate because of dipole-dipolar field. So this interaction has magnetic nature as opposite to exchange interaction. So it's weak, but it's long distance. So for spin waves with large wavelengths, usually dipolar interaction is of priority. And for very short wavelengths, exchange interaction plays a dominant role. Good. Now I would like to come back to electromagnetic wave and to explain you what dispersion curve is. Dispersion curve is, in the simplest case, if you are looking from the applied science, let's say, it simply couples your frequency of your wave with a wave number. And what is wave number is just inverted wavelengths, like it's shown here. So what does it mean? Let us have a look on the dispersion of electromagnetic wave. So it's kind of light, but for smaller frequencies. So here I use just a few gigahertz frequencies. These are the frequencies which are used by our Wi-Fi routers and so on. And you see that dispersion, for example, in air looks like this. This is just a straight line which goes through 0 point. And dispersion curve tells you very simple. I want to work with a frequency of 4 gigahertz. Then I just go here and I see, okay, for 4 gigahertz, my wave number will be a bit less than 1 radian per centimeter. It means the following. So if I want to know my wavelength, I just take 2 pi over this value. And I can say, okay, my wavelength here will be 7.5 centimeters for this frequency in air. Yeah. If I now want to send light or this electromagnetic wave through glass, you see that dispersion changes its angle. What does it mean? It means that this angle principally is defined as the group velocity. This is the speed with which wave propagates, which can be found simply as derivative df over dk. And in the case of electromagnetic wave, it's very easy. It's speed of light in vacuum divided by the refractive index. And you see that this is the refractive index for glass, this is the refractive index for diamond, and you see that your light or wave is simply getting slower in materials with larger n. But there is another parameter which is called phase velocity. And phase velocity, you see this here we have this derivatives, and here we don't have derivatives. So it's defined simply as this frequency divided by this k. And in the case of electromagnetic wave, like it's shown here, it's obvious that phase and group velocities are equal. What does it mean physically? Physically, it means the following. If you want to excite not continuous waves that you can't have non-stop source and wave just propagates and propagates, but you work in a way that you excite some pulse, then you have a wave, but besides you have envelope of this pulse. And phase velocity shows you how fast wave propagates itself. But group velocity shows you how fast it carries energy or information. Yeah, and if you have the same electromagnetic, the same velocities, then the picture looks like that. Phase and group velocities are identical. Good. So this was just electromagnetic wave, which you know very well. Now I'm switching to a spin wave. First, what we have to keep in mind about spin waves that it doesn't propagate in vacuum, because you do need this magnetic moment, so it means that you do need proper magnetic material, and that's why field of magnonics, so nowadays it's how we name field of science investigating spin waves. This magnonics is always strongly coupled to material science. We always need to search for better new materials where spin wave propagates faster or longer distances and so on. And the objects which we investigate, usually we speak about so-called waveguide. So waveguide usually has it's a film of some thickness, and it has some width, such as strip, and usually we consider it to be simply infinitely long. Besides, and it's an k, is pointing along, it means that wave is running just along this waveguide. And of course, we need to apply some magnetic field. For example, we apply it perpendicular to our waveguide. Good. In this case, you will get so-called dispersion relation or so-called magnetostatic surface spin wave. So there is a family of spin waves, but so this, yeah, good to know that all these title names. But what is important for us now that let us compare this dispersion with the one shown for the previous case of electromagnetic wave. You see here, I keep the same maximum frequency of 8 gigahertz. So I want to fix this coordinate more or less to the previous one. But if you will look on this scale, you see here this factor of 10 to the power 3 appeared. It means simply that for the same frequencies, spin wave has 1000 times smaller wavelengths with respect to electromagnetic waves. So if in the case of electromagnetic waves, we were talking about several centimeters, so here we are talking about several tens of micrometers, much smaller. But principally, spin wave wavelengths can be much, much smaller further. But if to come back to comparison between two dispersions, you also see that this dispersion is not linear. It goes like this. And final, it doesn't go to the 0 point. Yeah? 0 point is somewhere there. And what does it mean? In the simplest case, it means that phase and group velocities are not equal. For example, like it is shown in this animation, when wave runs faster than it carries energy. But another very interesting point about spin wave is that we have a possibility to change this dispersion strongly, and there are many parameters how you can do it. For example, what you can do, you can just change the orientation of the applied magnetic field. So it was perpendicular like this. And now you change it along like it's shown here. And what you see that, so now we are working here with another type of wave, not anymore magnetostatic surface spin waves, but backward volume magnetostatic spin wave. And you see that it even exists in another frequency range. So with these waves, you would work frequency above that one value. But for backward volume, you're working already with these frequencies. All these shifts can be shifted up and down with magnetic field. So this is just an exemplary frequencies here. But what's interesting for us now is that group velocity, which is just the slope of this curve, is negative. So it's very interesting situation when group velocity is negative and phase velocity is still positive as always. And then we have a situation that wave is running into one direction, but it carries energy into the opposite direction. Quite interesting physics. So we have investigated, for example, inverse Doppler shift and many other related phenomena to this. If to speak about all families of so-called magnetostatic spin waves, we should also, this is our magnetostatic surface spin waves, this is backward volume, but if you will magnetize the sample perpendicularly in such a way, then you also will have forward volume magnetostatic waves. So there are three waves, and what's important that these magnetostatic waves, principally these are waves with small key, and here we take into account only dipole-dipole interaction. Exchange interaction is not taken into account here. So this is just half of picture. Because if you will take into account also exchange interaction, all this, so this is the same MSSV and the same backward volume, with the difference that here I use now logarithmic scale in order to show also large key. And so these curves are like before, but just look different because of log scale. But if you go to larger and larger key, at some point, this angle between neighboring spins is not parallel anymore, and exchange interactions start to speak. And exchange interaction is much stronger, and it simply brings energies of all these dispersions up. And as I said, for purely exchange waves, dispersion is simply parabola, k squared. And that's how picture looks for, in general, for dipolar exchange spectrum of spin waves. And also you have always different thickness modes, or if you work with waveguide, you can have here many waveguide modes, width modes. So it's all interesting physics to study. But for us, it's also important that we said that wavelengths can go to microns, tens of microns, yeah, for these gigahertz frequencies. But now here you see I plotted wavelengths. So principally, we can work in wavelengths starting from millimeter and down to, for these frequencies, down to 100 nanometer, let's say, for this material. Nevertheless, we should not forget this is not end of the dispersion curve. It's just very beginning. It's more or less, all this is more or less a 0 point of the dispersion curve, because dispersion of spin wave in terms of wavelengths is limited by the lattice constant of your magnetic material, so this is atomic scale, and in terms of frequency, it finishes in the tens or hundreds of terahertz frequency range. Therefore, magnonics has very huge potential for the scaling down devices more, and for increasing their speed, simply moving more and more in that direction. Okay, so much about dispersion of spin waves. And now I would like to show you one example of real experiment which we do in our lab, that you have a feeling how does it look like nowadays. But before, let me briefly jump back to the harmonic oscillators. But instead of having one oscillator, I want to refresh your memories what happens if you have two coupled oscillators. Okay, so here we have two pendulums. As you know, pendulum, it's also just the simplest harmonic oscillator, as long as your angle of displacement here is not very large. But in this particular case, we have slightly different system, because you see these pendulums are not fixed here. They are hanging on such a wire, so this fixation is fixed, and this oscillator are on a wire, and it means that if as soon as you have some motion here, through this wire, it acts on second oscillator, and this one acts on the first one. In this case, we can speak about two coupled oscillators. Of course, there is already a theoretical model described behind it, so just as to give you a taste, the equation of motion looks like this, so it's similar to that what we obtained at the very beginning, but here you analyze now displacement or amplitude of oscillations from first and second oscillator, so you see they are staying in the same equation, for one for second oscillator, and besides here there are some parameters which are described, kinetic energy, and a parameters they described it, potential energy. But my message is that if you want, you can find in books this all well described. For us, it's important just to understand what is the physics behind at this point. And physics is very simple. As soon as you have oscillations, you see that at some point of time, like now, this one oscillates and this not. And after some time, this one oscillates and this not. So here you see amplitude of precession. You see now all energy is in red and nothing is in green. But after some time, there will be no energy in the red and everything will be in the green. So these two coupled oscillators just pump energy from one to another, from one to another. And this kind of physics, we started using spin waves, but on nanoscale, and we coupled not two oscillators, but two spin waves. And this was done on an example also called directional coupler. So what is directional coupler? Directional coupler is a device which is intensively used in microwave technique, yeah, for rotors and for so-called other microwave technology. And also it's used in photonics and everywhere. So its operational principle is very simple, that you have one input and two outputs. Part of energy goes here, part here, and principally it just distributes how much energy you can send in one and other channel. So here is written minus 10 dB, so it means that 10% goes here and 90% goes straight. And this also directional coupler was shown for spin waves on macroscopic scale. What we did, we just brought everything to nanoscale, and we have shown also fancy nonlinear physics, and we have shown how you can use this directional coupler to build computer. But today it's not a topic of this mini lecture, so let us just see how it operates. So that's here you see the structure under investigation. So it was developed by Martin Kaewenig, and the technology was developed also by Bernd Heinz. And in this case, here's the strip which you see, it's our magnetic waveguide. The size here is 350 nanometers. So if our hair diameter is 50 microns, so this is around 100 times smaller than hair. So it's really very small. You cannot see it with a normal even microscope. So this is our waveguide. As you remember, we just want to send a spin wave along this waveguide. Then what we want also to do, we want to excite the spin waves. For this, we put such antenna. It's coupled here, so just outside of the figure. It means that we send here microwave signal. And you know that when you send a current through a wire, it creates a magnetic field around Ørsted field. But now we send not a DC current, we send a microwave signal, for example, at a frequency of 3 gigahertz, which constantly changes its sign. When it constantly changes the sign of current, it also constantly changes sign of the applied magnetic field. And then we will get a system exactly like it was shown. You remember that animation where we were just exciting magnetization precession when we were applying such field, small field perpendicular to the H0, and we were able to excite spin waves. That's exactly what we are doing here. We just locally excite spin wave here, and then it propagates along this waveguide. What happens afterwards? This is just a one oscillator or one waveguide. But at some point, it reaches such a region where second waveguide is placed close to it. And these waveguides are coupled due to simplest dipole-dipole interaction, like two compass arrows. And it means that we principally have a system of two coupled oscillators or two coupled waveguides. And exactly like it was in the case of oscillator, they will start to change to pump energy from one to another. So what we expect is that energy from this waveguide will go to second one, or in some condition, we will see also jumping of energy back and forth. And afterwards, what we do, we just increase the spacing between these waveguides. The spin wave runs more, but here we have no more coupling. Distance is very large. And we simply can see again how spin wave propagates in individual waveguides. How do we measure spin waves? For this, we use so-called brilliant light scattering spectroscopy. We will not go into details, but the main idea is very simple. You just take laser, you focus it on your structure. Some photons are scattered by magnons, by spin waves, and propagate back. Then what we do, we just carefully collect all photons which are scattered, and we analyze them because they carry all information about spin wave. And principally, then you can, for example, scan all the structure and you will see what is the intensity of spin wave, for example, in different spatial points. But you have also time resolution, spatial resolution. So this is a very powerful technique. So Michael Schneider with Björn Heinz developed it, and experiment here, also person who did all this work is Chi Wang. And I will just show you this 2D map. So here you see the structure, as was in the previous, but on top is staying the BLS map of spin wave. You read it very simple. If it's red, it means that you have large spin wave intensity. And if it's blue, it means that there is no spin wave here. And obviously there is no magnetic material here, therefore there is no signal. And then you can clearly see that really, first of all, we excite spin waves locally here and it propagates. There is a damping, that's why it's getting more and more decreases its amplitude. But what's important that we see that really energy from one waveguide jumped to second one, and it easily runs to the output of second one. So you see practically nothing. So here I show you the intensity of spin wave average over this rectangular, and you see practically nothing. This is this waveguide, everything went to that waveguide. Or what you can do, you can change this frequency, and when you change this frequency, then you can control the coupling between of waveguides. In this case, the coupling is simply twice stronger, and that means that the distance which wave propagates when it couples its energy is twice shorter. So everything is, this pumping of energy back and forth happens faster. And here we observe that you can pump energy here and it can go back. So principally it means that, you remember these two coupled oscillators, we have shown situation one full period when we pumped energy completely to another waveguide and then we pumped it back. So this was the main idea of this work, and now you have a feeling how we work with spin waves nowadays. And at the very last slide, yeah, so it's gonna be Christmas time soon. Our nanomag group Christmas card is ready. So we all wish you happy holidays and happy new year. And with this, I would like to thank you for your attention.